Welcome to the AI Research Roundup. I'm your host, Alex. Today is May 8th, 2025, and we're diving into some fascinating new research. We'll be looking at an ICLR conference paper titled Emergence of Metastable Clustering in Mean Field Transformer Models, published on January 22nd of this year, so just over 3 months ago. This paper explores how simplified versions of transformer models, these are AI systems often used for understanding language, develop temporary groupings or clusters of information. The researchers use a concept called a mean field approach, which looks at the average behavior of many parts, to study how these clusters form and persist. They model the evolution of tokens, which are like individual pieces of information, using a type of mathematical description called a partial differential equation to understand these intermediate clustering phases, which are really important for how AI learns to represent data. Alright, so to help visualize this theoretical breakdown of how clusters form, the authors include a schematic diagram. This figure illustrates the 3 distinct phases they identified in the token evolution. It starts with a, quote, linear phase, where initial, small random variations begin to grow. Following that, there's a, quote, quasi-linear phase, where the system's development is mainly governed by a crucial number called Kmax, which predicts the number of temporary clusters. Finally, it depicts a, quote, collapsing phase, where these Kmax clusters actually form. This Kmax value is influenced by factors like the inverse temperature, often represented as beta, which essentially tunes the system's tendency to order itself. Alright, so building on how these phases unfold, this next plot gives us experimental insight into the duration of that quasi-linear phase. It shows this duration on the vertical axis against the number of tokens, n, on the horizontal. The horizontal axis is on a logarithmic scale, so equal spacing represents multiplications, not additions. And what's really interesting is that the red dots, the actual measurements, closely follow the dashed line. This shows the duration of this metastable phase increases with the number of tokens proportionally to the natural logarithm of n, or OLNN, which is exactly what their theory predicted for how long these temporary clusterings persist. So, we've seen how the theory predicts the duration of these temporary clusterings. These next visuals then illustrate how the number of these clusters is determined. On the left, we see graphs for 2 different values of the inverse temperature. That's beta equals 5 and beta equals 7. These plots show a quantity, gamma k, which helps predict the most likely number of clusters, Kmax. And indeed, Kmax is 3 for the first case and 4 for the second. The middle panels then show simulations of how these tokens or particles actually group together over time. And the right panels are histograms, which are like bar charts, clearly showing 3 and 4 clusters forming, just as predicted. Okay, so those histograms clearly showed the predicted number of clusters. Now these 3 plots here give us a visual timeline. They show how an initial state, where the tokens are spread out evenly, what's called a uniform measure, with just a little bit of random variation or white noise, evolves over time. This is for an inverse temperature of 5. You can see it starts out pretty even, then some waves start to form, and finally it settles into a pattern with 3 distinct peaks. This 3-periodic solution, meaning a pattern that repeats in 3s, is exactly what the theory predicted for this specific inverse temperature value. So, after seeing that 3-periodic pattern emerge, this next figure really quantifies that evolution. It plots the Wasserstein distance, which is a mathematical way to measure the difference between how the tokens are arranged at any given time. The solid lines show how far the current arrangement is from the initial, perfectly even spread. The dashed lines show how close it's getting to that predicted 3-cluster state. You can see the system starts near uniform, then clearly transitions towards the 3 clusters. And notice, even with slightly different initial random variations, shown by the alpha values, the overall journey is the same, just shifted a bit in time, which supports a key assumption in their model. Okay, so to understand how these tokens evolve, the researchers model their journey as a kind of flow on what's called the unit sphere, which is essentially a mathematical surface, like the skin of a ball, where all possible token states are located. This figure then shows an example of a curve, this black line, on such a sphere. It's labeled as being in H3, likely representing a trajectory or a stable pattern when Kmax equals 3, giving us a concrete picture of these abstract representation dynamics. So these trajectories on the unit sphere really illustrate the core findings. Essentially, this work explains how temporary groupings or metastable clusters pop up in simplified transformer models. It turns out that tiny initial random variations grow, leading to these clusters. And importantly, the number of clusters and how long they stick around, for a time proportional to the natural logarithm of the number of tokens, can be predicted. This gives us a clearer insight into how AI models begin to form representations. That's our AI Research Roundup for today. Thanks for listening.